And thank you. No, it's okay. Yeah, it's been a joy to visit, even though it's been short. Please do feel free to check in, via email, or if you happen to be in Baltimore at Hopkins or Space Telescope, please do give me a shout. I would love to meet up and chat more science. But I've had a great time here, and it's absolutely my pleasure today to tell you about two very exciting fields in astronomy today. And the first is studying galaxies and observing using wide area surveys, which give us unprecedented sensitivity and at large scale. And the second topic is the growing role of machine learning in AI, which, as we see, is transforming the way that we think about scientific discovery. And so I'm just going to get started with a roadmap of how the talk will look. First, I want to go over a little background, thinking about galaxy evolution and the role that we might use data-driven astronomy there, especially looking at the pixel level data that can be found in image cutouts of galaxies. So we're going to talk a little bit about convolutional neural networks, which are the tools for the trade for processing image data at scale, although there are others. And then third, I'm going to talk about galaxy formation on the low mass end. So honing in on dwarf galaxies, which are ubiquitous, but also sensitive probes of lambda CDM of galaxy formation at the extremes. And then finally, and hopefully I'll have time to really spell this out, is to say a little bit more about how we can think of representing galaxies and their large-scale surroundings with graphs and graph neural networks. Okay, so with all that said, I'd like to get started with the growth and evolution of galaxies. And so we know from simulations, for example, that dark matter collapses under gravity into these structures called halos. These are gravitationally bound structures or virialized. They continue to accrete matter. And so what you see on the left here in that yellow is like the projected density of this cosmic web of mass. And that the dark matter here is the only physics that are in play. So this is an n-body simulation. And of course, you can see that there are this clumpy structure in the middle, which is what we call a halo, or really a central halo. But there's also substructure. There are these smaller, sort of fainter little pinpricks. And some of those actually belong within, or orbiting within the around the halo of that central massive halo. Those are satellites. But aside from just gravity, we know that there's normal matter, baryonic matter, as we like to say in astronomy, which is shown on the right being simulated here. And you see the gas there accreting into the centers of that central halo there. And in fact, you're really zooming in on a smaller scale. We're talking about things like tens of kiloparsecs here, as opposed to the scales of tens of megaparsecs on sort of the image on the left. And so really zooming in, you find that there's these high density regions because you're allowed to let gas condense and cool, which allows them to basically achieve greater density, undergo runaway gravitational collapse, and eventually form stars through nuclear fusion. And so as those gas clouds cool and condense, right, stars are born. And that's exactly what we mean when we say that a galaxy is formed, right? And as it grows, it continues to evolve. Now, sometimes it's helpful to think more abstractly. If you just zoom in on a single galaxy, you can actually model the growth and evolution of a galaxy using this one curve. This is the star formation history shown in blue here, from early times on the left to some, maybe cosmic noon, where the star formation rate is very high, and then to some later point in time observation. And this is tied to the accretion of cold gas into the halo, really into the centers where it's dense enough to actually start forming new stars. And this star formation history is actually tied to another curve, which I'm going to call the chemical enrichment history. Okay, this is the rate of production of heavy elements over cosmic time. And you can kind of see that this red curve is following that blue curve. It lags behind it in time because those heavy elements have to be nucleosynthesized inside the stars, which have to be born according to that blue curve. Okay, but I'm actually an observer. So my training is sort of in observational astronomy, and I care a lot about what we can actually infer or measure about galaxies through observations. We obviously can't watch galaxies grow and assemble stars in real time over 13 billion years. So we could model in simulations, but from an observational standpoint, I think a lot about things like the star formation rate, which is that rightmost endpoint of the blue curve at the time of observation. We might care about the total stellar mass that has formed within the galaxy. This is proportional to the integral of that blue curve, right? If that's the star formation rate at every point in time, you can make some assumptions about an initial mass function, about mass loss rates. It's a very simplified expression, but it's something like the area under that curve. And similarly, the area under that red curve there basically the abundance of all the heavy elements that have ever formed relative to the primordial hydrogen in the early universe, that is something like what we call the gas phase metallicity, Z gas. That's what I'm showing there. It's basically like the area under the red curve, again, modulo tons of assumptions. And it's important to note that you usually have to use detailed observations like spectroscopy in order to derive or measure this last quantity, this metallicity. Okay. Now, since I said that this red and blue curve, the star formation history and the chemical enrichment histories are correlated physically, you might think also that their integrals should be correlated as well. And indeed, if you measure the masses and metallicities of about 100,000 galaxies, just like Sloan Digital Sky Survey did about 20 years ago, we find this tight scaling relation. This is presented by Christy Chimanski et al. Seminal work. Over sort of 3 orders of magnitude in stellar mass, you find very tight scatter in the metallicity of those galaxies, the gas phase metallicity. And what this does is it highlights the statistical power of these large spectroscopic surveys. We can really start to map these things out in terms of their physical properties, not just their observed ones. And in fact, this mass metallicity relation confirms that our very simple, toy model of galaxy evolution makes sense, right? It's intuitively following from the physics that we might think about. And of course, you can replicate this with better statistical models. You can use semi-analytic modeling, or you could use, models with more physics or more sort of empirical relations. All of those models are extremely successful. And yet, we haven't described one of the most important, or at least one of the most evident properties of galaxies, which is their beautiful morphologies. And we know that galaxies come in all shapes and sizes, right? And all the complexities that arise when you try to just categorize them very simply. This morphology of galaxies, which you can kind of see here in the Hubble tuning fork diagram, it's connected to and it reveals the ongoing physics and the past evolution of the galaxy. And I want to make the point that these images of galaxies are way more information dense than photometric catalogs. And this is a very boring, purposefully boring 2-column table of galaxies. They all have the same R magnitude. They all have the same G-R color. Of course, you need images. And in fact, these are the same images now expressed in terms of their pixels, right? This is so much more informative, and it tells you something about the past formation or the present evolution of the galaxy, kind of what phase of growth it's in. And finally, we have the tools to exploit this pixel level information. I actually just want to give another analogy, mostly because I have kids. I want to ask, does anyone know which fictional character TV show this is? This is the integrated photometry view, for the record. Now, let me go click the OK up here. I just realized it's blocking my stuff. No guesses?
Bluey.
Who said Bluey? Yeah, indeed, low res imaging is already pretty good enough, right? That is the actual average color profile. There's Bingo, actually, a little sister of Bluey. It turns out, yeah, if you add environmental parameters, you can do even better, right? So if you really want to know, what it is that you're describing, just integrating over a single aperture, spatially integrating over that light is not sufficient. Okay, good. So we're going to talk now about images and processing those images. I'm just going to skip over this and say that there is some motivation that is very loosely connected to biological neurons for artificial neurons. It's tenuous, though. In any event, we have input images that that we can represent as a grid of pixel intensities. So I'm going to call these X's. This is just to show you, like, convolution layers are really the way that I think of them is basically matched filtering in sequence, multiple matched filtering, nonlinearity, and doing that in sequence. And so when you take a convolution with a morphological feature, what that really means is that you have a second matrix, which corresponds to some sort of feature, some sort of shape, right? Again, think of those white boxes as just another image, but it's the image that you're looking for. And where these two images, or at least that subset of the image, is similar, you want it to have a high correlation value. And in fact, you're going to also apply nonlinearity. So in this case, if the correlation is negative, you throw that away. Okay, we can think of this as a activation, or so after the activation function, we can think of this as a map of the activations, or the map of the features, and where specifically they are found in that image. And so as you slide this window over the underlying input image, you are building up this map, this representation of where that feature is found. It's just like a matched filter algorithm. You can also control for edge cases. That's why the shape of this image seems to change. But in any event, the idea is that you can make these downstream maps of features based on the morphological feature finder. But that white matrix is not something that you hand, parameterize. You don't say, these are the features I'm looking for. You allow the data to try to find the optimal configurations of what these morphological features ought to look like so as best to represent this map of feature. And you can do many of these in parallel. You can also do many of these in sequence, and such that you feed in this map of features as the input the inputs to the next layer in your convolutional neural network. And so what this looks like is that you're sending these in as inputs to the next layer of convolutions, and you can search for more complex and high-level features. Maybe in the beginning, you've got things like, edge detectors, or you're looking for point sources. But hopefully by the end of this neural network, you've got like interesting things like in your galaxy data set, you've got spiral arms or dust lanes or H2 regions, the kinds of things that you would expect to see arise from the data. And then finally, you can just kind of get this list of features, all the types of features that were found within your image. They describe everything that's in the image, at least hopefully enough to solve the kind of problem of interest. You might think of this feature vector as a row in a table. This is kind of the intuition I have, where each image is now mapped onto a set of these morphological features. So you go from the pixel representation to some sort of morphological feature representation, which are the columns of the table. And these could be the things that you produce a photometric pipeline to extract for you, but for a CNN, it'll do it by its own, on its own. And then finally, by taking either a linear or nonlinear combination of these features, you can decide if you want to add more neural network layers. You can finally make a prediction in the supervised learning example. And to be specific, the kinds of things that I spent the early part of my career doing was just, that's kind of a joke now that I think about it. So long ago. But like, deep learning has evolved a lot, even just in the last 5-6 years. But it was kind of astounding to me that we could predict something like the gas phase metallicity just directly from color imaging. This is not something that was intuitively thought to be true. In fact, a lot of people told me not to bother because it was just not going to happen. And yet we can not only predict the gas phase metallicity directly from images, or even probe something like the H1, the neutral atomic hydrogen gas, and also use ways to interpretable machine learning techniques to basically understand where in the images these neural networks are looking at in order to make different types of predictions. But we can actually predict the entire spectrum of a galaxy, which is being shown in this kind of canonical example here, where you can just take the image cutout of a galaxy and in fact predict its optical wavelength spectrum. And we were able to validate that even in some sort of aberrant cases, which tells us something about galaxy scaling laws and whether the morphological relations that we learn via convolutional neural nets are actually still valid past a certain point, even in these anomalous systems. Okay, but I actually lied to you. I said something about how you can come up with these interesting interpretations of the features at the end of this network. But this is totally false. Actually, the learned features at the end of neural nets tend to be completely undecipherable, right? This is a major problem for scientific discovery, as well as actually for AI safety. You want to know what the neurons actually mean, and when they activate, whether they actually correspond to some sort of semantic meaning. People who build guardrails into large language models, they want to make sure that a particular neuron in your layer of a large language model corresponds to like toxic behavior, and then you can zero that neuron out, and then you don't have to worry about it anymore. And in our case, maybe we'll have a semantic meaning of a feature that is coming out of this galaxy image input, and it says something like, how strong are the tidal tails of the galaxies? In reality, it's not just represented as a single feature here. It's actually shredded across many neurons. And in fact, each neuron can contain fragments of many different features as well. So instead of being a one-to-one mapping of semantic meaning to neuron activations, it's a many-to-many mapping. In other words, it's an uninterpretable mess. Okay, so there is a technique for getting around this, and it's actually been used for a couple of decades in computer science, and this is called sparse dictionary learning. It's a way to basically get a network to consolidate its learned information into a small number of interpretable features, as interpretable as we can make it. And in that case, we're actually able to then train a model that makes predictions using a linear combination of more simple interpretable features. In this case, what I'm doing is as an activation function, I'm actually only choosing the top k highest activation in this feature and just simply taking the linear combination of those in order to make some sort of prediction. And critically, I'm actually training it with this in the loop. This is not done post hoc. This is done during training. So the gradients must flow backwards. In other words, you must adjust all of your neural networks so as to accommodate the fact that only a few features are being activated at any time. And what arises in this case, I'm going to show you when I apply it, is to add this image in. I'm going to go and restrict just to the top 4 activations for any given image. In other words, you need to design a vocabulary that can describe this image and any other image using 4 features out of a possible vocabulary of much more than 4 features, many, many features. And then with those, I want to predict, in this case, the spectral line fluxes of these 4 characteristic lines. H alpha, H beta, these are Balmer lines, hydrogen recombination lines, and then there's O3 and N2. These are sort of roughly able to trace out this parameter space over on the right there, can't find my cursor, where you're plotting O3 over H beta. This tells you something about the sort of higher ionization gas against N2 over H alpha, which is a lower ionization species. In other words, you're trying to understand what kind of physical process is exciting or ionizing the gas. And it tends to be that star-forming galaxies falling to the lower left of that quadrant of this parameter space tend to be down there, and I wrote SF for that. Active galactic nuclei, or accretion onto supermassive black holes, they tend to be on the right side, higher ionization in general. So there's a lot more subtlety here, but we want to see what this sparse feature net is able to learn. And it turns out that these features that fall right out are immediately interpretable. So let me just guide you again. Again, this is the O3 over H beta versus N2 over H alpha. This is sometimes known as the BPT diagram. This is like a way of diagnosing the gas excitation. Okay, and that sort of dividing line tells you the difference between AGN and down here star-forming galaxies. So these here, the highest activating galaxies are shown in white. Those sort of lower activations are shown in like a pale blue. And there are many galaxies with 0 activation whatsoever. They're not even on this plot. And the highest activations are shown over on the right, examples of those highest activations. And so I can use my astronomer intuition and say, these are definitely low metallicity dwarf galaxies that are maybe forming stars in their first starburst, their first episode of star formation. They seem to be low mass, low metallicity. And in fact, it's actually well known that galaxies that are in this upper left locus here are very low metallicity galaxies that often are dwarf galaxies. Okay, but there's no, a priori, there's no reason why the image would be aligned to the, the physical parameters in this particular way. Another sequence of highly activating features we find is these, which seem to be the opposite. These are high mass and high metallicity galaxies with older stellar populations. Again, this kind of falls out. And in fact, we actually really see this honing in on a subclass of these AGN, which are sometimes called liners or even liars, where it's unclear whether the low ionization ratios that are seen here, especially high N2 over H alpha, is actually just due to a lot of sort of older stellar populations as opposed to bona fide AGN activity. But anyway, the point is that you are seeing a coherent group, both morphologically and in terms of the physical parameterization of these. One more example here is actually high excitation galaxies. These actually look like extreme emission line galaxies. It's known that galaxies that are close to this dividing line here tend to be these starbursting galaxies, actually quite similar to the high redshift analogs of galaxies that are being seen by JWST and other infrared telescopes today. Those kinds of galaxies tend to be extremely compact, very high gas densities, and they tend to be indicative of extreme emission line ratios, which is kind of what we're seeing here. And if you look on the right, it's kind of clear that these are pretty irregular galaxies. A lot of them are either merging or have very strange morphologies. And in fact, this is actually a very interesting way to search for, in my opinion, galaxies that are leaking Lyman continuum emission, a good way to study galaxies that seem very similar to the ones in the early universe. So I think that this is actually something that warrants immediate follow-up study. And then finally, another sort of often activated feature is something that seems to reflect this diffuse star formation and has relatively low excitation. And these are just the 4 sort of highest or most frequently activated galaxy image features that came out of the SFNet while training. And one nice thing about the way that we've trained this is that you can actually just write down these line ratios as a linear combination of the activation strengths. In other words, you can, when I say that this is interpretable, it means that I can actually read off the coefficients and understand how does something like, O3 over H beta, which, for an observational astronomer, it means something really specific, and see, oh, this covaries in these kinds of different ways with these image strengths. I gave another example, which wasn't shown here, of how you can actually parameterize the gas metallicity just 2 parameters. And in fact, that performs just as well as if you use, a 500-dimensional latent space, more or less. So it's very interesting that you can really disentangle the neuron activations in those cases. Okay, that was one way to think about interpretability. Another method is actually this mechanistic interpretability toolkit that has been gaining a lot of traction recently, which is to map these dense uninterpretable features. We're reverting back to this picture where you have this sort of dense feature vector, and you actually map it into a set of sparse ones. And the way that we do this in sparse dictionary learning, specifically using sparse autoencoders or SAEs, this consolidates the dense features into just a few sparse ones by basically training this autoencoder here in yellow, which actually, again, only has a few activations that are non-zero. That sparsity constraint on the latent space of the feature vector. I know there's a lot of latents. This is the latent of the latent space, the real latent space, if you will, which is sparse and therefore actually maps to something hopefully more interpretable. And in fact, you can check out a paper written by some really enterprising students of mine last summer, where we did this over like loads of text data. And we actually found that this really works well. This is sort of over archive paper abstracts. We're able to basically understand the feature and the meanings of different concepts that were like learned and can be represented in archive papers. So you can look at that, but right now I'm just going to say a little bit about training these sparse autoencoders. If you have your input dense feature X, this is obviously in some relatively high dimensional space. You actually want to learn an encoder now into an even higher dimensional space, except that it's sparse. And this is a very, very simple architecture. I'm actually not sure why everybody uses such a simple architecture, but this is just what people do. And in fact, actually, this is what motivated the first part that I actually just showed, which is to use the full CNN and not a simple architecture. But anyway, you can take your input feature, you put it through an encoder, which then goes into some latent space. And then again, you zero out everything that's not in the top K highest activations. You then have a decoder, which is just a linear combination of those that reconstructs your input. And the hope is to have some reconstruction loss and the sparsity penalties such that you can essentially decompose these input features into a sparse basis, an over-complete basis, if you will, right? So there are many options, of course. It's a higher dimensional space, which is the important part. And all I'll say about this, aside from like being able to apply this to text data, is that, again, you can find that immediately interpretable features fall out, right? This is like, I downloaded the Euclid Q1 data, I just immediately grabbed a pre-trained model and just took a look at the highest activating features. And they're basically all interpretable in some interesting way. You've got smooth galaxies with, small neighboring little like guys nearby. You've got things that have these linear features, which I actually suspect is just diffraction spikes. You've got, face-on spiral galaxies, mostly barred ones, edge-on disk galaxies, and then this interesting scattered light pattern from Euclid. These are things that just fall right out of the data, right? And I think, obviously, this warrants a lot more attention. I should say more. I should try more pre-trained models and so on. But there's a lot of interesting applications here. And I think really communicating with our colleagues who study AI for a living has some benefit. And of course, we also have to think about the tools that they've developed for, for industrial like applications, which may not always be the best tools for the kinds of things that we want to do. So I'll just leave it at that and move on to galaxy formation at extremes, because this is a way where we can actually derive real value, operationalize these kinds of machine learning models. So to preface this, I'm going to drink some water. And I'm going to talk about satellite galaxies. So satellites, by the way, there are 2 satellite galaxies in this image, so you can go hunt for them if you don't want to listen to me. These satellite galaxies, often dwarf satellite galaxies, they orbit around the dark matter halo of a more massive central galaxy. And we know that they have to live a pretty tough life because these low mass satellites are so easily destroyed by all kinds of different physical processes, ranging from early cosmic reionization, which can just totally evaporate all the gas in them and they never even form. There can be star formation feedback where they form a burst of stars and then everything blows itself up and it's gone. You can get ram pressure stripping as these satellites enter the hot halo of a more massive central galaxy where the cold gas can get stripped apart. And they can be totally sheared apart as the tidal forces from the central potential also tears them apart. And so it's no wonder that they're really useful for comparisons to theory, because they're so sensitive to basically any type of physical ingredient you put into your simulation. And astronomy, historically there have been these problems, these missing satellites problems, where in simulations you have loads and loads of substructure, but then in observations you see a handful of satellites that as opposed to hundreds or whatever that should have been detected. And the similar related problem is known as the too big to fail problem, which is to say that, okay, even if you can somehow get rid of the most mass or the lowest mass satellites, the bright massive satellites should still persist. And in fact, there's too many of those guys as well. So something about the baryonic physics and the dark matter physics, something in there is not quite working right? This was the problem. And it turned out that modern simulations were able to address these problems by invoking baryonic physics. They just said that we need strong observational constraints, that can help us better tune things like star formation feedback or the baryonic potential or other parts of these simulations. And so there are different ways that we can basically start to meet each other in the middle in terms of how many satellites do we really predict, how many satellites do we really observe. Okay, and so in order to get a better handle on this, the SAGA survey, which is the Satellites Around Galactic Analog Survey, is one of the premier surveys that's really trying to confirm and perform a complete census of satellite galaxies around Milky Way-like systems. SAGA is basically leading the charge on getting a sample of satellites around Milky Way analogs at about 25 to 40 megaparsecs. And their goal is to basically take a spectrum of every faint pinprick of light around each one of these host galaxies. So here's your host galaxy, and out to basically the projective virial radius of this entire image, you look at every little pinprick of light that might be a dwarf galaxy and get a spectrum of it. And if its redshift is consistent with that of the host, then maybe it's a satellite galaxy. But if it's some distant interloper, and there are many, many more of those distant interlopers, then it's obviously not a real satellite galaxy. And so out of something like, I think, 75,000 spectra that were taken here, very, very rigorous observational campaign, we ended up with, oh man, it's covering it, 378 satellite galaxies down here. So in other words, something like a 0.5% success rate. Try writing that in your observing proposals. 99.5% impurity. And you're seeing here some of the examples of these low mass satellites, right? These are each satellites, and the full survey was able to find all the satellites around 100 host galaxies. And so this is an extremely complete survey, right? It's really like pushing the frontiers of how you want to spend your telescope time. And it's such an observationally rigorous one that we started to rethink, what can we do with this inefficiency, right? If 99.5% of the satellites are actually, or satellite candidates turn out to be background objects, maybe we can learn something about the nature of these satellites and use this to our advantage. So we trained a CNN basically on the low Z galaxies and the high Z galaxies. This is obviously not a very clean separation. There's no magic distance, at which low Z and high Z become really well-defined terms. But just for the sake of being able to make some sort of prediction, and clearly because we see a morphological distinction between actual low Z and high Z satellite candidates, we can actually make this classification from ones that are near versus far away. And in fact, we can then go and apply this across 20,000 square degrees of the wide area surveys. So we went out to the legacy survey and identified all these candidate low Z galaxies based on this training sample using only about less than 400 bona fide galaxies that are actual satellites. So this is done with like 5 million image cutouts. Again, we did a lot of number crunching, but ultimately we're able to go and identify loads and loads more satellite candidates. And let me just say up front that this method really does work in terms of following up CNN selected targets. You have to trade off your incompleteness for purity. And in other words, if you're making false negatives, then you can do so at the expense. You can basically improve your false negative rate at the expense of false positives and vice versa. And what we've done is we've gotten some time on the DESI basically the DESI spectroscopic campaign as a filler target program. So whenever they have spare fibers, when they're taking observations with the massively multiplexed spectrograph that DESI is, we basically have a hopper of candidates that can go in the mix. And we said, oh, these low Z candidates should be observed. And we had 3 selection criteria. There are techniques or tiers you can think of. There's the CNN tier, which is what I just described. And then there's two other tiers, which are shown in the purple and blue. These are photometric selections. And these are actually the ones designed by the Saga team. So this is like honed over 10 years of like expertise and really trying to make this as efficient as possible. What you see is that this is the photometric selection techniques are getting very low Z galaxies. In this case, Z less than 0.03 is the cutoff we used, is getting them about 1% or less of the time, right? The CNN, meanwhile, is getting about 20% purity here. So 20% of the time, we're actually getting very low Z galaxies. And indeed, the distribution, this histogram of the redshifts, as confirmed by DESI itself, actually shows that we are surpassing the previous photometric selections by an order of magnitude. But again, I want to make sure that you understand that there is a trade-off being made here, because now we have, we do have lots of objects that are not actually at high redshift, but we can actually characterize them because we know from our evaluation data sets what fractional of them are in fact not at low Z. So what do we do with this? In the meantime, like DESI is taking data. It's a 5-year survey. They're ahead of schedule. They just released a huge tranche of galaxies. And so we're really excited about that. But we also need to be careful because as DESI, a spectroscopic survey, is actually taking data, it actually doesn't give us all the fibers we requested. We have a filler program. So we have to model our incompleteness. And that depends as a function of clustering, which makes clustering studies really, really hard. So in the meantime, we can actually just go out and using our validation statistics, identify all the probable low Z galaxies with machine learning now. And so at redshift less than 0.03, previously known, there was about 17,000 low Z galaxies. And with this technique, which I'm calling XSAGA, extending the Saga survey with machine learning, we found 100,000 new ones. And you can see, just flipping between these two, that many of these are far, far fainter than the ones from before. And they do follow some clustering pattern, but it becomes a little messier because the tomography essentially that we're looking through the slices are a little bit different. Okay, so again, we are suffering from both impurity and incompleteness. So we're losing some low Z galaxies. We also get contaminated by some interlopers. But with DESI, we can actually characterize exactly what fraction of the time that's occurring. And so we can calibrate out the types of effects that those has on our downstream analyses. So let me go ahead and say some of the analyses we do, which is to take these probable low Z galaxy candidates, these faintest ones, and actually cross-match them if they belong in the halos of more massive systems, right? If they fall within the projected virial radius of a massive galaxy, then it's very probable. We can, again, quantify this, but we can see that they might be low Z satellite galaxies of those specific host galaxies. And so we find 10,000 satellite systems, candidate systems thrown here. And this is 100 times the statistical sample that Saga has gotten. It's also useful to actually inspect these data, right? You should always be looking at the data to ensure that they're actually, confirming or at least, validating according to what you expect. And in fact, what we find is like, for example, here's a galaxy close to the 0.03 cutoff in redshift. This is a host galaxy. It's about the same mass as the Milky Way. It has actually a low surface brightness, but relatively massive dwarf galaxy that's next to it. And then it's got a bunch of other lower mass dwarfs, which definitely would be hard to follow up through spectroscopy. On the right, you can see actually that there's two galaxies which are spectroscopically confirmed. This is something like a Milky Way, and it's got something that looks like a large Magellanic Cloud-like analog. But in fact, we find two more candidates that are plausibly also satellites in the same system. We can probe into environments that Saga was not designed to study, like the group environment. We don't really venture into clusters because there's just a lot more stuff going on there. But in sort of these groups, like, for example, in this galaxy system, NGC 5326, we can find lots of probable satellites. And including this bottom row here is actually a very interesting set of candidates. These are very red galaxies that actually would be very hard to confirm on the basis of their absorption features. In other words, these kinds of things are very often missed, but they're also extremely valuable for finding the quenched fraction of galaxies, around these sorts of Milky Way mass or higher mass systems, because they tell you something about, how often you expect to see, passive dwarf galaxies, which is something that the Milky Way has loads of. Other galaxies seem not to have much of, and we're not sure if that's an observational bias. In this case, we're starting to actually be able to see them, but of course, we know that we have other sort of errors systematically here. Okay, so this is how we're extending the Saga survey by 100-fold in statistical power. Let me just show you what some of the things we can do here is we can measure the satellite radial profiles. This is the number of satellites as a function of projected radius from each host galaxy. And here we've disaggregated the host galaxy sample by their stellar masses. And what we see is this trend marching upward. Of course, that more massive satellite galaxies or more massive host galaxies have more satellites. That's something that we expected to see, but has never been measured, with this level of statistical power. And furthermore, condition on the host morphology as well as the mass range of the host, which is being shown in the solid and the hatched markers over on the right there. You're seeing disk galaxies and ellipticals. We actually see this kind of bivariate correlation where you've got more satellites around elliptical systems, but primarily at the highest masses. So there's something a little more complicated going on when we think about the interactions of having both mass and host galaxy morphology here. Another interesting thing that we can probe is actually the dark matter halo accretion history. So looking at the magnitude gap on the x-axis here, this is the gap between the brightest satellite galaxy and the host galaxy. This is often used as a tracer of the last halo accretion event. It's something that, as you have more time since the last accretion event, you end up destroying some of those satellites, and you end up widening that magnitude gap. And what you also expect to see is that the number of satellites will decrease as a function of that time since the last halo accretion event. But what we can do in this case is actually precisely measure the slopes of these and how they covary with the stellar mass of the host galaxies, which is something that we can actually compare directly to simulations. And again, for the first time with this level of statistical power. I have a student who's been now looking at not just Milky Way analogs from the mass perspective, but also looking at ones that are in paired versus isolated environments. So these are galaxies that might look more like a local group where you have like a M31 and a Milky Way, two L-star galaxies, two massive galaxies, kind of within 700 or so kiloparsecs of each other. And we could actually even get statistics on this, not only on the number of satellites, in this case where we're looking at the stellar mass of the host galaxy, but also the G-R color shown on the right there, where we actually show, in fact, this is actually quite interesting, that you end up finding redder satellite galaxies around paired hosts than you do for isolated systems. And I'm not sure, we can fully claim that that's what we're seeing, but the early data are very consistent with that. And likewise, we can also condition on the presence of a massive satellite like the Large Magellanic Cloud. If you have an LMC analog, it turns out that you should have more satellites, but we can quantify how much. And you actually have this kind of more confusing, it's harder to interpret, connection with the colors. Like in some cases, they tend to be bluer and perhaps more star forming. In other cases, it's not clear that there's any difference. This is conditioned not just on the presence of a LMC analog, but also on the stellar mass of the host galaxy. So a lot of work to be done on these dwarf low mass systems. And I'm just going to shift gears a little now and in fact talk about galaxy surroundings. And really returning to this picture, we've been talking about galaxies and satellite pairs as if they're kind of evolving in isolation. They're in their own halos, maybe a sub-satellite enters the halo, but then we're just leaving it alone. We're letting this sort of star formation history stay put, as just a single curve. But we know that galaxies undergo interactions, right? These galaxies merge, they bring in fresh gas and for new star formation. And they're also, the galaxy evolution is subject to the broader environments. And so it's helpful to think a little about sort of the wider scale here. And the gravitational influence for a typical Milky Way galaxy is something like 300 kiloparsecs. This is known as the virial radius. But the typical separations between galaxies of around the Milky Way mass is about like 3 megaparsecs. It's about an order of magnitude larger than the virial radius. So it's not an unreasonable assumption to say, they mostly evolve in isolation and do their own thing with occasional catastrophic mergers. But the physical effects actually are more than just the major mergers, right? We know that the galaxies, when they fly by and they have their mergers, they can bring in gas, they can torque the systems and actually rearrange the distribution of gas. And in fact, the large-scale environments, even early in the universe, and the energy that might be injected from supermassive black holes or early star formation in the universe can preheat, the gas in the surroundings, which changes how much gas can be accreted into these galaxies at later times. And all these kinds of effects do depend on the large-scale environment. So we want to know, how do these large-scale environments affect the galaxies that live in them? And even before we get there, we really want to ask ourselves, what is the best way to even quantify environment? there's a couple of contenders, okay? One way is quite simple. It's to measure the mass density in some set radius within a sphere. And this is just known as the spherical overdensity. This is a very simple way. You just add up all the mass within that sphere and you say, maybe you normalize it by the average density of the universe, and you've got, your dimensionless overdensity parameter. Another way to do this is through an algorithm or set of algorithms that revolve around topological data analysis. The most well-known one is called dispersed discrete persistent structure extractor. And it's kind of got a simple, like, you can think of this kind of simply, right? Like if you think about like what is the most overdense region, which would, and what is the topology of that? It's the same question you would ask yourself if you're standing at the top of a mountain. You say, how do I know I'm really at the top of the mountain? Well, you look around you and you say, okay, well, the gradient is negative in every direction. I'm on the top of the mountain. You have to smooth those scales too. So, if there's like a little rock next to you, you don't say, oh, that's the top of the mountain. You just say, no, no, no. On average, I'm at the top of the mountain. You're on the ridge between, two mountain peaks. If you look ahead and behind you and you see that, okay, the gradient is positive in those directions, but then sort of to my left and right, it's negative. And this is the kind of same argument you can think about finding filaments or finding, the nodes, the clusters, and so on. The idea is that disperse is supposed to be able to extract these kinds of different topological features. And so this is another good way to keep environmental structures or to basically measure them. Okay, and I want to pose this question specifically: what is the best way to quantify environment in light of the stellar halo mass relation? So the stellar mass and the halo mass, that's a way to connect the baryons and the dark matter, is a way to inform us of galaxy evolution. And so if environment is informative about galaxy evolution, then dark matter environment, this large scale environment, should help us be able to paint on the correct galaxy properties onto just the dark matter halos. So that's how we're setting up this problem. And specifically, I'm going to talk about results in the illustrious TNG 300 simulation. So given a subhalo and its large scale dark matter quantified by one of these two techniques, how much stellar mass are we expecting to reside in that halo? We, in this case, use an explainable ML technique, which is kind of similar to a tree-based approach. It's called explainable boosting machines. If you're familiar with abundance matching, it's actually kind of similar to that, except that it's sort of easier to quantify the contributions from all these different features. And so we've got a bag of features that we're interested in. Dark matter halo features. These are things that you measure directly from each halo or subhalo. As I said, we can measure the overdensity on 3 megaparsec scales. And we also have all these dispersed cosmic web features, like distance to the skeleton, distance to a cluster, distance to saddle point, of varying, basically saddle points and so on. And on the y-axis here, we're quantifying SHAP importance. This is the Shapley additive explanations. Basically, this just tells you how much each feature contributes to a model's prediction. I can say more about the details, but it's sort of a way to fairly sort of distribute, the prediction significance to each of these parameters. And what we see on this log scale is actually that aside from the dark matter halo features, which we know are the primary indicators of the galaxy halo connection, that actually the simple overdensity is the parameter of choice for really quantifying large scale environment. And so this is actually really interesting that such a simple technique is actually telling you a lot more than a couple of these other sort of, extracted features from topological data analysis. But I want to keep going. Is there a better way? And in fact, this last strategy I want to present is to basically take every dark matter halo and construct a giant basically construct a big point cloud where each of these subhalos are in this 3D space. And we can actually create a graph by connecting halos to their neighbors if they're within a specified distance. Okay, so then you can write down your cosmic volume actually as a collection of halos, which are nodes, and their connections, which are edges. And so it looks something like this, if this is for a smaller sub box. And what we can do then is take, this cosmic graph, and you can basically paint a GNN on it. You can train a graph neural network to propagate information around on not just the nodes, but also the edges, the connections between nodes. So in other words, you can update, you can have a halo update its own node representation. You can have a GNN layer on the edge between a halo and each one of its neighbors. You iterate over its neighbors, and that's a function of the two halos properties. And you can read out that information from the edges back onto the halo itself. I know there's a lot of technical details that I'm omitting here, but there, I would say that if you're interested, you can look at these two papers that I wrote. But just returning to the question then, again, what is the best way to quantify environment in the context of the stellar mass halo mass relation? What we find is that, in yellow, this is a model with no environmental parameters, just purely dark matter halo terms, basically abundance matching. We can compare that against the dispersed cosmic web parameters, which doesn't really have a characteristic length scale. We can change the characteristic length scales of the spherical overdensity, which we get the best results at 3 megaparsecs. And we can actually do the same thing for the graph neural network. And what we see, obviously, is that the environment does make a difference. It does help you reduce the error in terms of predicting the stellar mass. But kind of very impressively, is that the GNN is able to flexibly learn information, in particular on very large scales. It seems like it's continuing to get better, even as you expand the graph connectivity. And it's able to basically learn a lot more about how these stars or how the baryons should be mapped on to the dark matter only representation. So the takeaway here is that the way that you represent your data really matters. Graphs, have a lot of nice characteristics. They're permutation invariant. You can make them, invariant or equivariant to the geometry of the system. You can naturally restrict that search space using the symmetries that describe it. And really importantly, the halo catalogs that we're working with, they actually naturally fit onto this graph representation. So I really urge you, to think about, right, just as when we have images, we said that a convolutional neural network is kind of like a nice fit for the data type. In this case, thinking about graph neural networks before a point cloud data set is the natural fit. And then just a really quick teaser is actually we can not only make graphs in environment, but also graphs over time to characterize, for example, the merger history of galaxies. This is work led by Christian Jespersen. And what we're finding actually is that there's a lot of redundant information. In fact, to within error, actually totally equivalent information between environment at a late stage in the universe and the merger history over the entire merger tree that we can try to parameterize. And that seems to, again, in the context of the galaxy halo relation, tell us something about where that information might be arising from. So that's also preliminary work. I probably should have slapped that on there. Okay, good. So I see I'm running low on time. What I'm saying, all I want to say is that we have these current and future wide area surveys that are rich with imaging data, and we're excited about this because we can finally extract that information and capture it, and use it in better ways. These convolutional neural nets are really good at figuring out galaxy properties, and in fact, I would say that there's a degree of interpretability too that we can gain when we do this. And using these neural nets, we're able to capture an unprecedented number of low Z dwarf galaxy candidates. And we can immediately go out and do science with those in the low redshift universe, as well as follow them up as we are doing with DESI, so with real spectroscopy. And by the way, this has already produced the largest spectroscopic sample of those low mass galaxies ever. And I think when the survey's done, it should be almost an order of magnitude higher. And finally, by using this explainable ML techniques and to think about representations of galaxies, we can also really link galaxies, halos, and their very large scale environments together and really teach us about how we can maximize the data from these upcoming new space telescopes and the cutting edge algorithms that ML and AI is affording us. So thanks for listening.
Great. We might have 4 minutes before the Uber gets here. Questions, Mike?
I have a really quick one. 3 slides back, you showed that environment up to 10 megaparsecs is relevant for getting stellar masses, but it keeps getting better. Have you pushed that to when it turns over?
Well, I haven't, and it's primarily because you start to lose, not really be able to sample the box very well of the simulation. It probably is worth a try. I haven't done it, but yeah, it might be interesting.
If you get that gigaparsec, it shouldn't matter.
Yeah, so we definitely can't do that because it's a 300 megaparsec volume, and we sort of reserve a part of this, torus for validation. So we have to be very careful with how we stratify this, how we leave buffer zones and stuff, so we're not cheating in any sort of way. We don't want to be propagating information since now we are throwing the environment in. Yeah, I could maybe go out to like 20 or so megaparsecs, but at that point you're in the linear regime or getting close to it. So I think it's also kind of interesting to think about, whether you really expect anything to be quantifiable beyond whatever, sigma 8 scales or so. Right.
Thank you. That was a fantastic talk. So I think you showed very compellingly that the morphology has information about the metallicity, about the ionization, and so on. I was curious if you could tell us more about, so what do we learn about the kind of like fundamental physics of what's setting the mass metallicity relation then, right? Like based on this experiment. So is your CNN learning the fact that, I don't know, like galaxies that have undergone recent mergers and maybe like slightly more disturbed, they have some kind of metallicity reset, or like, so I was curious more about kind of the physical interpretation of why this is so successful, right? Like, are we like implicitly learning to predict mass basically, and that's why we're predicting metallicity?
Right.
Are we like, yeah,
so I can answer, we're not learning to predict mass. That is something that we explicitly checked, and we say if we can predict, how well can we predict mass, and then can we like try to, learn the mass metallicity relation, and we do not do well there. It's hard to say exactly, and I think there are a couple of ways that you might try to get at this. One of the things that, one of the ways is by inspecting failure modes. Another way is to try to just like learn other weird deviations from known scaling relations and try to learn the residuals there, right? So I don't have the plot here sadly, but there's one thing where I look at the SFR M star relation, this, kind of galaxy sequence, main sequence, if you will, and looking at deviations from that and trying to understand the morphological characteristics that go with that. And so what you can see there, for instance, is that starbursts are giving you temporary large excursions from the star forming sequence. And it's harder to interpret exactly what's causing quenching or deviations in the negative direction. But those are the kinds of things with more follow-up, I think, allow you to at least open the door for that. These extreme excitation galaxies are also, I think, another interesting point of follow-up, but you kind of have to go through them one by one. I'm not sure that we can say much except that morphology or something in the imaging domain is telling us about the physics. We really need to figure out what it is, though.
All right, I think we might have to cut it there, so he doesn't miss his flight. So please email him, he will respond probably on the way to the airport. That's been John again.
Okay. Thank you so much.
It's a lot.